So our first stop on the integral calculus of vector fields is the idea of a line integral. And so the first of the activities in this section really is just intended to get us used to the concept of what it is that a line integral, or sometimes called a path integral, actually measures. Like what should it mean to integrate a vector field, and what kind of a region, domain of integration should we be thinking of when we think of a vector field. And so the motivating activity, the preview activity in this section, is going to ask us to imagine the idea of a line integral from the point of view of the concept of work coming from physics. So in physics, work is an energy transfer from one system into another system. So for example, if I pick up an object like a pen or whatever and I drop it, that in the process of falling, energy is being transferred from out of the gravitational field into my pen. And it causes my pen to gain kinetic energy as it accelerates toward the desk, right? And so there's an amount of work that's done on the pen by the gravitational field in the process of that pen falling. And so you don't have to be, you don't have to have a physics background to really wrap your arms around what's going on with line integrals, but it does kind of help. And so that's the metaphor that we're going to live in for this introduction for the preview activity. And so the setup is this. We're flying in an airplane, and that airplane is flying through a wind velocity field. And so the question that we ultimately want to ask is, how much work is that wind velocity field doing on the airplane during the flight? If that amount of work is positive, it means that generally during the flight, the wind was a tailwind. So the wind was actually kind of helping to push the airplane in the direction that it was going. If the work is negative, it means that generally it was a headwind during the flight, and so the wind was kind of resisting the airplane in the direction that it was going. If that number ends up being zero, then it means that the wind was generally neither helping nor hindering the airplane in the direction that it was traveling. So that's kind of how we set the table for this. And just to remove some of the calculus aspects of it, we're going to think of the wind velocity field here as being a constant. So the wind is blowing due east at 45 miles an hour. And we're going to measure everything here in miles. We're going to measure everything in hours. So we're not being, SI unit scientific about this. And so in parts A and B, we're imagining that we're going to fly this airplane 300 miles from some starting point at a heading of 20 degrees east of due north. So that would be called bearing 020 if we're flying in an airplane and using aviation coordinates. And so the question is, how much work is done on the airplane during that segment of the flight? And then in part B, the plane continues from that point and flies due north for 275 miles. Find the work that's done on the airplane during that second hour of the flight. So just to get a picture of what this looks like. So here is our wind velocity field. It's pointing due east. So everywhere in the XY plane, my vector field arrows are pointing directly to the east. And they all have the same magnitude, 45 miles per hour. So I'm measuring here as my units are hundreds of miles. So this velocity vector being 0.45, 0 means 45 miles per hour due east. So no matter where we are on this map, the wind is the same, right? 45 miles an hour facing due east. And so on the first leg of this plane's journey, we're going from some point, I'm going to call it the origin 00, and flying a total of 300 miles on a bearing of 020, so 20 degrees east of due north. So we end up right here at the end of that leg of the journey. In the second leg of the journey, we start from there and we take 1 hour and fly due north for 275 miles. And so after the end of the second leg of the journey, this is where we are. So part A asks how much work is being done on the airplane during this first leg of the journey, where we're 20 degrees east of north. And then second part is how much work does the wind do on the airplane during the second leg of the journey, where the airplane is flying due north. One of these is much quicker to answer than the other, but let's open up that preview activity in your activity streams and get started. And the key geometric idea of work is that work is supposed to measure the parallel component of the force that goes in the direction of the displacement. And so because of that, the dot product ends up being the algebraic tool that we use to compute an amount of work. So the amount of work that's done by a force F moving an object with a displacement of v is just the dot product of F with v. So with that in your toolbox, parts A and B are just asking to quantify how much work does the wind do on this airplane during these two legs of its journey. So to get us started, we found that the amount of work done by the wind on the plane as it flies at a bearing of 0 to 0, so 20 degrees east of north, and it flies for 300 miles, that the amount of work done, the dot product of the force and the displacement, is the product of the magnitudes times the cosine of the angle. So this is the way to find a dot product if you don't want to go into components. You just know, if you know the magnitudes and angles of the vectors, you can use this formulation of dot product. So since the magnitude of the wind is 45, the magnitude of the displacement is 300, and the angle between them is 70 degrees, because 20 degrees east of north makes a 70-degree angle with the due east direction, which is 90 degrees east of due north. And so the dot product is 45 times 300 times the cosine of our angle, so it's about 4,617. So if we look at the image, the picture of what's happening here, let me ask, why do we think that it makes sense that 4,617, the amount of work that's done, is positive for this journey? It's based on the picture that we're seeing here. Why is it reasonable to expect that a positive amount of work was done on the airplane during this journey from the origin out to that point? Since the dot product of force and displacement is positive, remember that the dot product of two vectors is positive exactly when those vectors make an acute angle with one another. Right? And so the vectors are more pointing in the same direction than they are pointing in opposite directions as one another. That's kind of how my heuristic on that. And so in this example, can we tell from this diagram, from the picture, that that is the case? If we're flying from the origin out to this point, then my velocity vector is pointing kind of 20 degrees east of north as I go along, and the wind is pointing to the east. And so the angle that those two make with one another is 70 degrees, right? It's an acute angle. Mm-hmm. And so the wind is more helping the plane to get to where it's going than it is hindering the plane to get to where it's going. Because the scalar component of the wind in the direction of our travel, in the direction of our velocity vector, is positive along the way. And so we get a positive amount of work that's done on this leg of the plane's journey. So then the next step is, what about on the second leg of the journey? And on the second leg of the journey, the plane is going to fly due north for a period of 275 miles in total. So what do we think about the amount of work that's going to be done on the plane as it flies due north for that length of time? So when our plane is flying due north, the angle that the plane's velocity vector, which points due north, makes with the wind, which always points due east, that angle's 90 degrees. Right? So the plane in the second leg of the journey, which we're calling C2 here, the plane is flying perpendicular to the wind. And so the wind during that leg of the journey is neither pushing the plane forward, it's neither a tailwind, nor is it pushing the plane against the direction that it's trying to fly, a headwind. It's a pure crosswind is what an aviation person would call it, right? So the wind is neither pushing the plane toward its destination nor pushing the plane away from its destination. It's just pushing directly across. And so the dot product of the force with the displacement, because the force and displacement are perpendicular, that dot product is just going to equal 0. So the wind has done no work on the plane or against the plane as the plane gets to its destination on that second leg of the journey. And so that's one we don't even really need to do a computation for, because if it's true that at every point of the journey, the vector field is perpendicular to the direction that I'm traveling, then I know that at every point, that vector field is not going to be helping me or harming me. It's not going to be doing any work on me, and it's not going to be doing any work against me in trying to reach my destination. So the total amount of work that's done on by the field on me is going to be equal to 0. Okay. So then here's another question. If we consider the entire journey from start to finish, so from my original point to the point that I ended up with here, call that C3. What do we think is going to be the total amount of work that would have been done to get me from the beginning point to the ending point? Let's just sort of talk through this one together rather than sending you into your breakout groups. So on the one hand, if we add up the amount of work that was done on the first leg of the journey to get to this point, which was 4,617, and the amount of work that was done by the wind on the plane during the second leg, which was 0, then to get from my starting point to my ending point, the wind would have done a total amount of work of 4,617 plus 0 to get to where we were going. So 4,617 in total. The question, though, and this is, I think, what they want us to do in Part C, is what if we had flown directly from my starting point to my ending point, instead of flying out here and then taking a left turn and flying north? What if we had just gone directly from 0, 0 out to this ending point? How much work do we think would have been done? What would be a reasonable guess, just a naive guess? Like, what do we think would be the case if we just flew directly to our destination instead of making a stopover over here? What we would love to be the case is for the amount of work that's done when we fly directly to our destination is the same as the amount of work that was done by the wind on us if we made the stopover along the way, right? And it turns out that in this case, that answer is going to be yes. Right? In this case, it doesn't matter how we get from 0, 0 out to this point out here, whatever its coordinates are. It doesn't matter how we get from point A to point B. The amount of work done by the wind on us is going to be the same, regardless of which way we take to get to our destination. So even if I had flown some wacky like spiral path or something taking me way out here, as long as I start in the same place and end in the same place, we expect for this wind velocity field is going to do the same amount of work on us regardless. But that is kind of an open question. Like anytime a mathematician sees a phenomenon like that, the question is, well, is this guaranteed to always happen? Or is there something special about this example that we're working with that makes that work what we call a path-independent quantity, right? It only matters where we start and where we end. It doesn't matter how we get from start to end, that the amount of work is the same. That's called path independence. So is that going to be the case in general for any kind of path integral, or was there something special about this example that we did here? So that's where I want us to sort of wrap up this first preview activity rather than work through the rest of these parts with that sort of tantalizing question of, when are line integrals guaranteed to be path independent? Is it always? Is it only in certain cases? Was there something extra special about this example that made that the case? And an answer to that is going to emerge as we work through the rest of this section.